infinite limits.
Oh, don't blow my head again.
So now we're wondering what happens when x gets very, very large as x approaches infinity. What happens to x squared? Now, in your textbook, I believe that your textbook, whenever an answer goes to infinity, it's like infinity is not a number. It always says the answer is undefined. However, in most calculus, we are concerned about knowing whether it is going to infinity or going to negative infinity, or if it truly is undefined. So I'm going to show you a couple of different examples. This one, what we're going to write, as x gets really, really big, what happens to x squared? It gets really, really big. It gets to be a really, really big positive number, so we're going to write infinity. Your textbook may say undefined. I'll give you some worksheets as well where it actually has things defined as infinite or negative infinity. Okay? Because I can have sometimes, like you remember the volcano graph that you did at one time? 1 over an x squared graph, so it has an asymptote right here. Let's say this asymptote is at x equals 2. I would say in this case, the limit as x gets close to 2 would be infinity, because it goes to positive infinity from the left side and from the right side. But if I had, a 1 over x graph with an asymptote at 2, this one I would say is undefined, because one part goes down to negative infinity, the other part goes up to positive infinity. So we're going to look at what happens when we get really, really big. And when we write our answer, we're not only concerned about positive infinity and negative just infinity, we're also concerned, does it get to be a really, really big positive number or just a really, really big negative number? In this case, as x gets really, really big, this one we would say it goes to negative infinity. Doesn't have to be x, and it doesn't have to go to positive infinity. What's going to happen to this as you go to negative infinity? It's going to go to negative infinity. Because a negative cubed would still be negative, and the value would get larger and larger and larger. Abstract-wise, if you had any power, and that power, the r value, was bigger than 1, as x gets bigger, so would your whole function.
If it's smaller, then you'd have a.
If it was smaller than 1,
You never get, you should be between 1 and.
Look at 0, x to the 0 is 1.
x to the 0 is 1. We have some different problems. If you have fractions, you have some issues there.
Just ignore it.
What happens in this case? Gets really, really close to 0.
So n is assumed to be 0, then we're going to infinity?
Hmm?
N is always assumed to be going to, starting from 0, going up to infinity, never from negative infinity?
It wouldn't matter what value you started from. It's just saying you're ending by going towards infinity. So it's not a notation where you're starting at a value. Like you might be thinking of iterations in computer science where you start at 0 and then do 1, then do 2, then do 3. This is just saying what happens as it gets very, very large. All right, maybe you worked ahead already. What's going to happen with this one? It's going to equal 5. So this part here, as n gets really, really big, is going to get close to 0. And 5 minus 0 is going to be 5. So in general, and I think I've changed this. Did I change it to n in your notes? Okay. So you have an n here. It really doesn't matter. If r is a bigger number than 0 and you keep getting larger and larger and larger, your value is going to get closer and closer to 0. So a couple of ways we can do this. One, we're going to do it algebraically so we can use our 1 over n strategy. The other way is you can think about the highest power that's there and understand something that you've graphed before. So first of all, I'm going to connect it to something you've graphed before. You graphed 2x plus 3 over x in grade 12. It was a graph that had a horizontal asymptote. Where did that horizontal asymptote appear?
2.
At 2. And what that showed us, that as x got bigger and bigger and bigger, it got closer and closer to 2. So maybe you remember graphing this in grade 12 and saying, I have a non-permissible value at 0. So I would have had a vertical asymptote at x equals 0. And in this graph, I would have a vertical asymptote, a horizontal asymptote at y equals 2. If you plugged in some points, for example, if you plug in 1, you're going to get 1 comma 5. If you plug in negative 1, you'll get negative 1, negative 1. And this graph looks like this. So from the graph that you graphed in grade 12, we're saying as our values of, in this case it's n, but it could be x if we used x there. As our values of x got bigger and bigger and bigger, what does our graph get closer and closer to? It gets closer to 2. So that's using what you knew from grade 12 mathematics. If I wanted to simplify this equation, what I could do algebraically, limit as n goes to infinity, is I could factor out an n out of the top. Can you see that that would give you 2 plus 3 over n all over n? And that would allow me to simplify these n's, and this limit just becomes the limit as n goes to infinity of 2 plus 3 over n. What happens to the 3 over n as n gets really, really big?
0.
It goes to 0. That's sometimes easier to see. 0 plus 2. This is equal to 2 that way as well. So we have an algebraic way that we can go about finding this, and we have a graphical way that we can go about finding this. The reason that this happens, I don't know, do people still play Monopoly?
Oh, yeah.
Have you played Monopoly?
Ruins friendship.
Okay, it ruins friendships. When you play Monopoly at the beginning of the game and someone lands on Baltic, now Baltic's one of those purple ones right at the beginning, and you own it, they owe you $4 of rent. And you make sure that they pay up at the beginning of the game. You're like, you owe me $4. It's like intense.
Yeah, but at the end, it's like
At the end of the game, when you've got hotels on Boardwalk and Park Place and houses on St. James and all over the place, but you still own Baltic with nothing on it, and they land on there and it's $4, you're like, just forget about it. It's not a big deal, okay? It's exactly how the game works. Because later on, you got like, someone just paid me $15,000 for landing on Boardwalk. Oh no, you can't go that high. 2,000.
oh, yeah.
It's 2,000.
I wish
Oh, no. So,
Yeah, so as you get really later in the game.
So now we have one we want to find the limit for, and it doesn't fall into the realm of, oh, I graphed that in grade 12. Okay? You did not graph x squared minus 3n cubed over 8n cubed plus 1. Okay? And some of you might, yes, as Ramsey noticed, be able to figure out the limit just like that. Now, the monopoly story that I was telling and where it connects to is when x gets really big, what's going to be the most powerful thing here? Cubing, right? Cubing is going to make, like, when you square 9, I mean, it's 81. That's pretty big. But if you cube 9, it's going to go to 729. Much, much bigger. And that's only at 9. What happens when you're at 1,000,000?
So it doesn't matter what the other one is.
So when you get to 1,000,000, that n squared is like that Baltic Avenue. It doesn't matter anymore. You can kind of ignore it. And if you ignored everything except for the highest power on the top and the highest power on the bottom, that's what you get. And that simplifies to just -3/8.
How would you handle?
Now, algebraically, to show that, if I wanted to show that algebraically, I could say the limit as n goes to infinity, I could factor out that highest power. I'll take an n cubed out of the top, leaving me with 1 over n minus 3. And I can take an n cubed out of the bottom, leaving me with 8 plus a 1 over n cubed, and have those n cubes simplify. And now when you apply the limit, 1 over n is going to be 0. 1 over n cubed is going to be 0. And you'll get -3/8 as well. So on quizzes, if you are able to do this mental math and just say what it is because you recognize the largest power, that's fine. If you want to show the algebra, the strategy is factor out the highest power. And in university, they might require that you do this and say some theorem that says 1 over n is 0 by theorem 6.2, 1 over n is 0, or something like that, and in order to explain it fully.
What theorem do we need to know?
You can just write it down. So part of the nice thing about taking calculus in high school, we're about introducing these ideas to you. In university, they may go more in depth and require a little bit more formality at certain points. You might even have to prove why some of these things work all the time. We're not as focused on those proofs, but just getting that idea. And the nice thing about having the idea is when you get into university and you have to prove it, you'll at least know what the answer is going to be and why. Okay? So you're not as bogged down with trying to figure out the proof as well.
How do you do the next one?
You have one of two options. Can you see that it alternates between being -1 when it's odd, +1 when it's even? -1 when it's odd, +1 when it's even.
0?
So this one does not exist. Does not exist. It has to come to a value. It's not possible. Undefined does not exist. It's fine.
It's so cool because it's weird because if you go infinity plus 1, infinity plus 2, it keeps.
Well, and let's say we wrote out these terms. You started with, let's say I start with 1, and then I subtract 1, and then I add 1, and then I subtract 1, and then I add 1, and then I subtract 1. And I kept doing this forever. How much would I have?
1. I've seen this. I swear.
Yeah, but I know 1 or 0.
It's 1/2.
Yeah.
People claim it's 1/2.
Okay.
There is a proof to it, but
What is it?
Well, I mean, some people would say, well, you should do this. If I group these together infinitely and just solve the
Who
brackets,
says that you're going to have an
what would it equal? It would equal 0. Okay?
Other people
So you're going to give me $0. No, that's not a good idea. I don't want you to give me $0. I'm just going to, oh, let's take these away. I'm going to do this. Add those ones, then add those ones, then add those ones. Then this is 0, 0, 0, plus I have 1. So you're going to give me $1. Again, it does not exist because we have different ways of thinking about it, and it alternates between 0 and 1, 0 and 1, 0 and 1. So it depends on where you end. What happens when n gets really big and you have 1/2 to the n? It is also equal to 0. Anytime that fraction is less than 1, it's going to equal 0. And this connects to something you did with infinity in grade 11. Do you remember your geometric sequences? The sum to infinity of them? It only worked, you could only find the sum if this value in there was less than 1. So this was something you had as part of, and I think I corrected this on yours, did I? This should be n?
How do you make those mistakes?
Oh, it's... So if r is less than 1, and with absolute value of r, because we can't just say r is less than 1, because then we could get like a -3, which wouldn't work. This is equal to 0. And last one, what happens when x gets really close to 0?
Because it's 1 divided by a really, really small number.
Okay.
It's
Very
close
big.
to infinity.
Why does this one not exist? Infinity is the right idea. Well, no, but you can get close to 0.
Because you'll never get to infinity.
The reason this one doesn't exist is from the right-hand side, sure enough, it goes to infinity. But what happens from the left? It goes to negative infinity. Because there's an asymptote on that graph right here. That one's tempting. Technically, our brains tend to think positively. We're positive people, that's a good thing. That when you do 1 over 0, you think to come from the positive side. And yes, it would go to infinity. But because from the left-hand side, it is equal to negative infinity, this one does not exist.